So we'll let a couple of people in, and then okay, so welcome everyone to the second afternoon session of Koka, and we'll lead things off with Dan Lyon, who will tell us about algebraic effects for functional programming using functional programming.
Thank you. Yeah, so I'm going to talk today, and this kind of talk, I'm very excited about it because you know, you get a little jaded over the times, but now I really feel the fire again. And why did it happen? Well, a while ago I went to a great how do you call it, seminar in Dagstal, thanks to a few people that are sitting right here. And I was very grateful for that, because I went there, they were talking about algebraic effects, and then suddenly I saw the light, and I was like, this is actually really cool. And when I went home, I was like, this is what I'm going to do. And why did I get so excited? Well, I think it has strong theoretical foundations. I love that. That's why I did functional programming in the first place with the lambda calculus. And I realized their algebraic effects are neat because they really emphasize the operations, and secondly, they're freely composable. So I see them as better monads. Don't tell anyone. Because I was, especially the composability really was attractive to me, because I was working on a language called Koka, which used monads to define user-defined effects. But we had real trouble composing them in an easy way for the user. And I saw that with algebraic effects, I could get this composability for free for a small price. No, wait, for a small price, I could get them almost for free. And finally, there was something that's maybe important, maybe because I'm at Microsoft. I often talk to people that are really into JavaScript or C# or other kinds of languages. And you see in these languages that they implement all kinds of control flow, especially for a specific use case. So for example, in C#, you see they have exceptions. There's iteration at a certain point with yield, and then now, or a few years ago already, they added async await for asynchronous programming. And especially the last one comes with a very complicated compilation scheme and interaction with other features. And now you see in JavaScript community, they're doing the same thing. So recently they added yield iteration, the function star, and now in the next version you will get async await too. And these are just very specific cases of some handlers that you can implement generically with algebraic effects. And I really feel that we should kind of, as a community, show them that, look, you should do algebraic effects, and then you can do all these things without always modifying your compiler and language with very complicated compilation schemes. So one thing I'm trying to do, actually, during this talk, my first half will be showing these kind of patterns with algebraic effects, and kind of as which should appeal to hopefully a wider audience. So then, right, so I went home and I thought, this is all great stuff, and then I implemented all of this in the Koka language. So I removed the monadic effects that I used to be working on, and I thought I'm going to replace this with algebraic effects, and it worked out really well. So there's a real full implementation of this. So Koka is a strict functional language that starts out with a total functional core, and then from that infers all effects of all functions, including divergence and exceptions. And now you can add your own exceptions, your own effects using algebraic effects. And it has a row polymorphic type inference to do all of this, and it had this already, and it turned out that algebraic effects fit in there really easily. Like it's a very natural fit. The thing that was actually really hard, and it made me look a long time before I actually started on this, is that we need a very, I would say, a non-subtle CPS translation to make this all work in managed platforms. And that's really important for me. In particular, I wanted to compile to JavaScript, because the goal is to write highly robust asynchronous web servers, and they run on Node, and it needs to run in JavaScript. But also if you would compile to .NET or the JVM or these like rich ecosystems and you want to take advantage of that, you need to have some way of compiling all of this. And that's a real tricky problem. So that will be the second half of my talk. Hopefully, if I hurry up. Oh, and if you want to learn more about Koka, actually nowadays you can download it very easily and build it and then play with it. So if you go here, this enormous link, or Google Koka book down, you'll get there. Maybe I even have. I'm not going to bother. But if you go to that web page, you'll get a nice overview and there's all kinds of stuff. Let me see. Little primer on Koka syntax, because I guess not everybody has used it, although you should. It's a beautiful total functional programming. What more do you want? So there's a few syntax things that I want to show, because then later you understand all the examples better. So one thing is I love to use a dot, because I can pretend to be an object-oriented programmer to wider audiences. So here you can see the dot just passes the first its first argument as the first argument to the function that's on the left. That didn't come out well, but you can see what it does. It works out really well. So if you write 1, 2 list map increment, it translates to map over the 1, 2 list the increment function, and then all associates to the left. So then if you do dot head after that, then you pass that as the first argument to head. So this works really well in practice. I really like that. And then the other thing Koka does, it has lots of support for functions, of course. It has nice syntax for dealing with anonymous functions, which you can write as just as between braces. You don't have to write a fun keyword in front. And then also if you have arguments that are functions, you can, just like in Haskell, you can just use white space. So the first is a while loop. While I bigger than 0, then to do the next the action argument, and that's really just calling while with 2 arguments, and that's really calling while with 2 functions that take no arguments. And I think what a nice thing is, and it's very important, Koka makes a strong distinction between values and computations. So everything that's a value will not have an effect, and only functions compute and they can have an effect. And if you have something like a while loop, you can see that in contrast to other languages, usually these are, in while, these are like little parentheses. But that's really pretending, because in Koka it's clear that if you call a function with parentheses, the arguments are evaluated at that time. But if you pass it in between the braces, you can see, oh, maybe this is a function, a suspension I'm passing in. This may be called never or many times. Like in while loop, you'd rather evaluate this every time you do one step of the loop. All right, so that's Koka. Let's go to maybe one more thing about Koka. So Koka is a truthful language. So for every functions, it infers an effect too. So it says a square is a function, takes an integer, and it delivers an integer, and it's total. So when it's total, you can also leave out the word total. So then it would just be int to int. But what it really means is that if you look at its semantics, you can model it with a semantic mathematical function from 32-bit to 32-bit numbers and nothing else. On the other hand, if you have something like error, which raises as an exception, well, then your mathematical function will look something like this, where you can return either a value or an exception. So it's very, when you look at the types of functions, they're now complete. They give you not just the input and the output type, but also its effect, so how you would actually model it in reality. So most languages, like say C# or something, they can modify the heap, and pure means, in contrast to total, it means you can diverge or raise exceptions. So usually when programmers have to reason in those languages, you have to reason about the signature that looks something like this, like there's an integer and some heap that you don't know about, and then you can raise exceptions or modify the heap or not terminate, etc. Which makes it much harder to reason about that. Finally, algebraic effects. So I want to explain algebraic effects like in a more practical way, because I'm a practical guy. But these would kind of be how you would look at the semantics of algebraic effects. And depending on how you look at it, you get a very different feel for what it means. So I personally like the first bullet's look, which says, well, algebraic effects, your operations, there are your algebra. And from that, you can create a free monad. And free monads are freely composable. And with the free monad, you get when you would execute a program with such operations, you kind of get a tree, and then your handler is a fold over that tree, and that gives you your semantics. So that's very neat, and that's just beautiful, I think. But a more practical way is saying like, well, algebraic effects and handlers, they're just resumable exceptions. Like you can kind of throw your operation and handle it somewhere, and then you can resume where you left off instead of just quitting. So both are fine to look at it, and for this talk, I will more look at them as exception handlers. So let's look at that. We already saw it this morning. Leo stole all my good examples. Where is Leo? Oh, there he is. Great minds think alike, Leo. So here's exceptions in Koka with the new algebraic effects extension. So you have an effect declaration, and I say that EXC are my new exception type. And there's a raise function. I say this is like defining your operation that takes some string and then, well, can return anything. And then here's a semi-safe division that says, well, if the thing I'm going to divide with is 0, then I will call this operation divide by 0. So now I still have to give a semantics to it. So I can look at the type of safe div. Let me actually show that. So I'm going to start a live demo. How dangerous is that? There we go. This is the Koka interpreter. Nice red on black background. Smart then. And then I'll load my module I wanted to load, common. And then I'll look at the type of safe div. And you can see that it inferred that it takes two integers and it maybe have our new exception effect. Right? So that's a nice thing. So now how do we get rid of the effect? Well, what did happen? All right. We're gonna handle it. So here I define my own catch function that says give me an action and some handler. And I'm gonna handle action. I mean, so action will be an anonymous function, it will be called, evaluated, and every time raise happens, the handler will be invoked. And it says, oh, if a raise happens with S, then just immediately return with whatever the handler function returns. And this is just how you expect exceptions to be. So the nice thing about the catch is that it says, okay, give me an anonymous function, the action, that goes to that has maybe our new exception type in it, and maybe more exceptions. This is the row polymorphism. And the handler that itself has the same kinds of effects possibly as the action, but not the exception we're handling. And then the final catch has handled the user-defined exception type, so it doesn't show up anymore. So it's polymorphic in the other effects that may happen. It's kind of nice because I could pass in a handler that itself calls raise. And this is why the row polymorphism in Koka is somewhat special because it allows duplicated effect types in the rows. But it goes too far. I will not talk about that. Let's look at a slightly more interesting handler. So here's another handler. So I can write, when I write handler, I really write an anonymous function that says, well, give me some action and handle that action with the handler I'm giving. So it's a function, so that's a value, because functions only compute if you call them. So if a value, it's the 2 may be a value, and it's a handler that says, if you raise, well then just return the algebraic, the nothing type. And if you return with a value without calling any operations anymore, then we wrap it into the just. And then we converted a function that may raise exceptions into a maybe type. Well, let's actually try something out. Well, we'll do, so here I do 2 may be. Let's type carefully. Oh, and then it takes an anonymous function. How nice. I can just do a little brace here, and then I call save div, and let's divide by 0, right? And then a maybe type comes out. So let's default that maybe type to 42. So default takes a maybe type and unwraps it, and then 42 if it's nothing. So hopefully it returns 42. Whew, wow, amazing. This is what algebraic effects can do. And let me actually show something else that's kind of nice. Because it generates JavaScript, you can actually run this in the browser. So if I set the host to the browser, I can run this amazing program in the browser too. There we go. 42. It's amazing. Yes, so that's actually really nice. Let's set the browser. Let's set it back to Node, where I'm running it on the prompt. So then, yes, resuming. So exception handlers didn't return, but in general, you can actually resume algebraic effects. So if I have a operation like getString, I can handle it by saying, oh, resume where you left off, and as a result, you give the string there. So if I write here s equals getStir, and I wrap it in this particular handler, then getStir will be handled by this guy, it will resume it there, so it will assign there to s, and then print hello there. We can run this one all way, what was it? Always there. What was the function? Hello. Oh, I can. Hello. Hello there. Amazing. So, I'm running already out of time, so I'm going to skip state. But in general, you can do something interesting, like with state, it's self-parameterized with some state s, and as get and put, and then you can do a little counting function where you have get and put, and then you can write little handlers. And the nice thing is these handlers can be parameterized themselves. So then you have a kind of a local state, which works really well. And you either resume with the same state and you're the result of that state, or you put in a new state and you return unit. So the resume can have more arguments. I'm going to skip a little further. So here's a funny example. This is iterators. So in C# or JavaScript, all very special compilation strategies and stuff. But with handlers, we can do it ourselves. We can just say, oh, we make a new effect that yields values of A. And you can call it the yield operation with some item A, and then returns unit. And then here's how you would iterate a list. So you would say, oh, if it's cons, we yield the X, and we call ourselves recursively, and keep yielding. And have a yield A effect in its type, and otherwise just unit. And now people can just write handlers and do something with any computation that yields values, right? It doesn't have to be over a list, it could be trees or anything really. So this is how you could do kind of lazy programming. So here's a for each, for example, that says, what does it say? Yeah, give me something that yields, and then I apply f on each of these values, and when you return false, I break. So when we return at the end, well, we just do unit, we're done. But as long as this action yields, we're going to do f on it. And if it returns true, we're going to resume, going to keep going where we left off, and otherwise we stop and return unit. And this is nice. And also another thing, it's kind of lacking in normally when people when languages implement iteration, is that the breaking of the iteration can be done by just not resuming. So often in other languages, you have to do here something like should I break equals yield X, and then the breaking of the loop is kind of up to the iterate instead of up to the handler. It's like turned around. So this is very, very nice. You can do this in such an easy way. And then of course the one I'm really interested in, because I want to write Node.js robust servers, is asynchronous operations. And these are a little special. So in Koka they're kind of more built in, and I'll show you why. So in Node.js you have these primitives that says, there's an asynchronous readline primitive, and it says, give me some function, a callback, that I will call when readline is done for you, and then it just does unit return. So the idea in Node.js is that you write readline with your callback, and then return to the outer event loop. You should kind of like quit your program, and then at some point in the future, suddenly this callback will be called. And this is what people call, callback hell, or when you look at many Node.js programs, you get this pyramid of doom with like a nested sequence of these callbacks. And we'd like to get rid of that. So we can do async as a regular effect, and then we have a very special handler though. And what the handler does, it's like outside your main loop, because it has to interact with this outer event loop that's provided by us, by the Node.js environment. And we're gonna kind of pass our resume function as our callback to that outer function. And then you get beautiful asynchronous programs. I actually show you one. Let me see. Here's a nice one. So here it says name equals readline, but readline is really an operation that will actually, it raises the operation, and the outer handler around main will catch it and pass the resume function as a callback. And then when it's done readlining in the Node.js environment, it will come back right here through the resume function and continue with the result. So you could have many, say, HTTP requests that all do this, and they're all interleaved with each other. So if I run this one, it will be just like as if it would be synchronous, because there's nothing else going on. I'll just do it for fun. Main, Dan, I'm 34. Hi Dan, you're 34. So it just worked, but it didn't do any asynchronous. I have actually one more example that I'm going to show. So here's one that's really asynchronous, just to show you it really works. So it says, well, do these two things synchronously. So here we do the read line, and over here we wait 3 seconds, and then we print done waiting, and it will return timing instead of the read line effect, and then we'll show both things. So if we do this, async hi, and I'll comment out Dan. Oh, it was so quick. So I could like wait first 3 seconds, and then it's done waiting, and that was asynchronous, and in the meantime it could have been typing Dan, and it would be hi Dan timing. But it's truly asynchronous in that sense, and it is a very beautiful way of programming this if you have algebraic effects without any of the callback hell that usually ensues. Whoa, I have only 5 minutes. Okay, I totally, So I need to change my talk on the fly, because otherwise I never get to the other interesting part. So I'm going to skip the semantics, I think. Yes, I'm going to skip this. So these are new kind of semantics that I really like, which are, it has a beautiful operational rule for handlers, which I think is very insightful and can really help you think about these things. But I'm going to skip over it. It's just too much. It relates beautifully with delimited continuations, and you can show that delimited continuations can be expressed as handlers in a very nice way. But this is what I wanted to show quickly, is that we're going to compile to managed platforms. In Koka case, all what you were seeing was in JavaScript. But the problem is you need to capture the stack when you want to resume an operation. Because just like exceptions, your operation gets raised, but since we can resume, we have to restore our execution context. So the way to do it on a managed platform is to compile your whole program very specially, so it all gets compiled to like a CPS transformation. So if you have the counter function we saw earlier, internally Koka translates it into this function. So it says the get operation will get a continuation of what it has to do next, instead of being assigned. And now the continuation is always completely explicit, and you don't need to capture the stack anymore. And that's how you get around these limitations in the managed platforms. And it was so much hassle to get right. but I can't see any other way to compile general algebraic effects to manage platforms. If, on the other hand, you control the runtime system, you could do it by actually explicitly capturing stacks. So there's something special going on here that was very important for Koka. That is that it's a type-directive CPS translation. So the continuation passing style only happens for things that are using user-defined effects, but not for other things, like the if statement and the print line, or anything that doesn't use a user-defined effect will not get translated. And here it's very important that Koka, when it infers the types, is truthful, because it uses those types to guide this compilation scheme. And if I would cheat somewhere, everything will not work. So it's very important to have a truthful type inference here. I need to almost stop, right? Let me see. Right, so it's type-directed selective CPS translation. And there's one problem that occurs with functions that are effect polymorphic. And what happens is that if you have no other information, just the polymorphic effect, you don't know, is this using a user-defined algebraic effect that I need to compile using CPS translation, or is this just using non-algebraic effects, and can I compile it more efficiently? And if you're polymorphic, you wouldn't know what to do. You basically have a choice. Well, I'm out of time. So what we do in the end is we pick a specific runtime representation where the continuation parameter can be detected if it's present or not. And for every polymorphic function, we generate two versions. One that's plain and usually more efficient, and one that's CPS translated. And we switch back and forth between CPS and non-CPS that way very nicely. And it seems to work out quite well in practice. And it helps a lot for efficiency too, because most of the time, like if you have a function like map, you can kind of inline the worker wrapper optimization by Simon PJ. You can kind of inline the wrapper and then immediately get the efficient worker if you're lucky, and that can be optimized further. Thank you very much for listening.
We have time for one or two questions. Simon.
So, I agree with all you say about Monas, but one of the things that Monas does kind of behind the scenes is it kind of sequentializes things, right, in a way. And in Koka, there's a kind of defined order of evaluations, right? And that's very important for knowing these effects occur sort of before, whatever that means, those effects, right? And so, somehow that you didn't really emphasize that, but that's kind of crucial piece of fabric, is that there must be a defined order of evaluation and a sort of semicolon operator. That's sort of built into it.
Yes.
Does that mean that you're starting from an inherently rather sequential computational fabric? And you have to go special, rather than pure functional programming. You might think, whoa, I can evaluate my program in parallel. Oh no, you can't.
Well, in Koka it's even total. But right, if you want to be pure, it may raise exceptions or not terminate. Then there is no algebraic effect, right? So you could evaluate in many ways. But what you're saying is
depending fundamentally on a defined order of evaluation for every construct.
Right. Just if you have the algebraic effects, now it does become important. Yeah. So your question is really, how should this work, algebraic effects in Haskell? And I'm not sure if I can answer that. I haven't thought deeply enough about that. Maybe Sam, I see Sam.
It's okay, Sam can answer. Right?
So Dan's previous implementation of Koka was monadic. And it had exactly the same property. He didn't have to write bind to return because it's a strict language with a well-defined evaluation order. Mm-hmm. This is completely orthogonal to the question of whether or not you use pronouns or algebraic effects. It's really about whether you have a defined evaluation order. He could do the same thing you do in Haskell with algebraic effects and have some special way of saying, this is the order I want by dividing some sort of
You need a way to say, this is the order I want.
Yes,
Yeah,
of course you do.
And you'd like to do that without saying it's a monad, because we don't want to use monads, right? So we need some other way to say it.
If you want to apply this in Haskell, then you need something like
Or indeed in any language in which you want it to be open about evaluation.
Yeah, but the advantage of doing it this way is you don't have to write all the noise.
Yeah, that's
Right.
fantastic. I'm envious, you know.
Because you keep track of total, you can evaluate any way you want once you know it's total. I mean,
Right, that's true, yes.
Yes.
Because you know you're pure.
Okay, so this was an excellent question. Took a bit longer.
There was a good discussion.
So we'll move on to the next topic.